Hey, welcome to video 22.2. We'll be looking at Coulombs Law in this session. Now, a basic idea with Coulombs Law is that it describes forces between charged particles. And you should know that like charges repel and opposite charges attract. That gives you the direction of the force. But the equation describing the magnitude of the force is the one you know is kq1q2 over r squared, where q1 and q2 are the two charges, or rather the magnitudes of the two charges. And r is the distance between them. And we're assuming them to be point charges, which is a pretty good assumption for most of what we work with. And we'll see some where that's not the case, but for now we'll just work with point charges. Because the direction is given by like charges repel and opposite charges attract, the sign of the charge does not actually go into this equation. So that's what it means when q1 and q2 are the charge magnitudes. They're always positive even if the charges themselves are negative, because the negative charges, negative or positive, would tell you the direction of the force, which is separate from this equation. Now in this class, and in your textbook, we'll frequently, instead of k, we'll use the expression 1 over 4 pi epsilon 0, but it's the same thing. K is equal to basically 8.99 times 10 to the positive 9th Newton meters squared per Coulomb squared. Epsilon 0 is 8.85 times 10 to the minus 12 Coulomb squared per Newton meters squared. Epsilon 0 is sometimes called the vacuum permittivity. And we'll see where that 1 over 4 pi epsilon 0 comes from and why it's more convenient sometimes than just writing k later. And you'll notice that Coulomb's law has a 1 over r squared in it, just like gravity. And that means that just like gravity, it produces stable orbits, which is why everyone thought that maybe electrons orbit the nucleus, because you've got positive and negative charge, inverse square. Newton already proved that you can get stable orbits from that. Turns out it doesn't work quite like that, but it's close. And almost everything we know about gravity can also be applied to electric charges. Now the idea of superposition. So we've got three charges. We've got Q1, we've got Q2, and we've got Q3. And let's figure for a moment that they're all positive. Now, we'll call this distance here R13, this distance R12, and this distance R23. If we want to find the force on Q3, all we have to do is find the force from Q1 and the force from Q2, and then add them together. So the force from Q1, because they're both positive, it'll be repulsive and point in that direction. The force from Q2 will point that way. And the net force will be the sum of those two. Use a parallelogram. And the net force on Q3 will be roughly like that. And you could get numbers, and then you break it up into components, add it that way. But basically you just add the forces as vectors. Nothing too terribly difficult conceptually, but the details can get quite thorny sometimes. Now here's an example of what you would do. Let's say you've got point charges Q1 and Q2. They lie on the x-axis at minus a and plus a, respectively. How should Q1 and Q2 be related for the net force on this third particle plus q to be 0. So right there is the origin. Here's plus a, here's minus a, and we've got q1 here, q2 here, and that charge plus q located there at a over 2. Now if we look at the forces on plus q, for the net force to be 0, the two forces have to point in opposite directions. And that means that either q1 and q2 are both positive, or they're both negative. I'm going to assume that q1 and q2 are positive. And that means that the forces on plus q will be, there's F2 and there's F1. And in order for the net force on q to be 0, plus q to be 0, these two forces have to be equal. And so now we can get expressions for F1 and F2. Now F1 is k times q1 times big Q divided by the square of the distance, which is 3/2 a. So 3a over 2 all squared. Whereas F2 is k times q2 times big Q divided by the distance between big Q and q2, which is a over 2, a much shorter distance. And so we set these two equal, we get kq1 big Q, and I'll simplify the fractions a bit. No. Four over 9a squared equals 4k q2 big Q divided by a squared. And now I can start dividing both sides by big Q, which is interesting because it means that any charge that we put at that location will experience no force. K is a constant, 4 goes away, so does the a squared, and you end up with q1 equals 9 times q2, which tells us a couple of things. First off, it tells us what we already know is that q1 and q2 have the same sign. It also tells us that q1 is 9 times as big as q2, which makes sense because it's 3 times farther away. Force goes as the square of the distance, so if you triple the distance and want to keep the same force, you need to increase the charge by a factor of 3 squared, or 9. Tomorrow I'm going to check questions 2 through 4, and we're going to get started with electric field next.